Hello everyone and welcome to another video for AP Computer Science. The main focus of this video will be relational operators and Boolean or logical operators that can be used in conjunction with one another. So let's go ahead and make a new class in our package basics, and we will go ahead and make a Java class. We will call this relational and logical. I'll just call it relational and logical. So we have to make our main like always. Get rid of my comments. And so what is a relational operator? These are operators that we've seen before. You've used them in mathematics. They're essentially the way we compare two numbers. So if you ask yourself, what are the different ways that we compare numbers? We always say things like, oh, one number is greater than another number, or less than or equal to, or not equal to. So we're going to say there are about 6 primary relational operators that we use in the Java programming language, and most programming languages have some equivalent. There might be a few extra, and how they're written might be a little bit different, but generally speaking, we're going to stick with these 6 relational operators. So I'm going to go ahead and put some notes. We'll say relational operators. And again, why are they called relational operators? Because they give us some sense of the relationship between any two numbers or values in our language. Compare values and return a Boolean. Well, let's say compare content, I guess. Well, no, not content. What's a good word? Not values. I don't want, because I'm going to use the word values. We can say they compare. Wow, that's hard to say. We'll stick with values. Compare values, often numeric, and return a single Boolean value. Okay, I'll stick with that. Right, the idea is that we might compare literals, we might compare variables, we might compare arithmetic, some combination. At the end of the day, whatever the content is, it's a comparison between two things, and the relationship, the result, is going to be a Boolean value, which means, if you remember, there are only 2 possibilities, true or false. And that's a pretty big deal because everything can be boiled down to a statement, almost like a statement of fact. Right? We would agree that certain facts are either true or they're false. And without getting into the philosophy of all of that, generally speaking, that's what we tend to do for a lot of things. And so it becomes very easy to express our reasoning and our logic to a computer in that format, in a yes or no way, because this very much mirrors the kind of early stuff that we saw, the binary, ones or zeros, right? On or off, electricity flowing or not. So the ability to make a decision, yes or no, or true or false, is a pretty big concept that kind of permeates the entire language, and so relational operators are one of the ways that we make this happen. So what are our operators? We have, I'm going to put the words and then I'm going to put the symbol. So the first one we'll stick with is less than. And that's easy. The less than symbol is the same as math, so the arrow pointing to the left, right? We have greater than, and that's the open side pointing to the left, or the arrow pointing to the right. We have less than or equal to, less than or equal. And so in this case, so normally in math we might have the operation blended together. It's a less than symbol with a straight line underneath it because it's a mix of the less than and equal to symbols. Unfortunately, most American and most keyboards in general do not have that symbol as a single character on our keyboard. So we use a pair of symbols together, very much like the compound operators. We don't put spaces, just like with those we do not put spaces, and so we will say less than or equal to. And so it looks like an arrow, and I've used these kind of like reverse in my notes, but this is the actual operation, is less than or equal to, and so it's in that order. Greater than or equal to, same thing in this case, and it may seem odd, but we're going to follow we're going to be consistent, and we're going to say greater than. It's not as pleasant looking, but it does mean greater than or equal to because it is a left to right binary operation, and so we're saying is the left thing greater than or equal to the right thing, and that's helpful. And then the last 2, and these are the ones that are maybe less common, though we typically do use them, equal to and not equal to. So we'll say equal to. Now here's the problem. Typically when we say two things are equal, we use the equal sign, right? In math, that's what we often use. But our equal sign has a very specific meaning in this programming language. It means to assign a value on the right side of the equal to the variable on the left. And even though we've seen already one example of context-sensitive operations, for example, the plus we saw could be addition, or if a string is involved, then concatenation, right? The blending of two strings. Unfortunately, the equal sign is so important. Assignment as a concept is so very important that it's not going to be able to be used in two different contexts automatically, right? The context is one, and so we have to have a different operation for it, another symbol. And so in this case, we use two equal signs. So you might hear me say equal, equal. I don't know why I do that, but it tends to be a very common way of saying equal, equal, meaning are they equal in value? Not an assignment, but a comparison. That's the difference, right? One is an assignment, two is a comparison. And then the last one, not equal to. And so for this one, again, we're going to see why the not operation is what it is. And so in math, we might say, oh, it looks like a symbol, an equal sign with a slash through it, and that's a pretty reasonable thing. So this might be a good guess. Slash equal. That's not a bad guess, but we've seen that this is actually a compound operator. This is divide and reassign, right? I'll take a variable, divide it by some value, and then reassign it back into that same variable. So we cannot use this one. Another good guess might be equals slash. That's a pretty good approach because you can kind of imagine that you don't blur them very much to the greater than or equal to and less than or equal to. And so, but that is not really how it's going to work out. And so what we're going to use is we're going to use exclamation point equals. And we'll see that when we get to our logical operators, exclamation point does basically mean not, right? The negation of an assignment. So here we're saying is the thing on the left not equal to the thing on the right. And that's a true or false statement. So let's go ahead and try making some values. And again, every single operator returns a Boolean value, true or false. So now if we're going to make a variable to hold some examples, it's going to be a Boolean variable. We'll call it Boolean and we'll call it eval. And let's start off with something simple. We'll start off with just pure literals. That's not unreasonable to do. And so let's make a statement. Now again, I am not stating a fact. I'm essentially asking a question. A comparison is a question that has a true or false answer. A comparison, yes or no, is it true that 7 is greater than 11? And if the answer is true, then that's what's stored in the variable. If it's false, that's what's stored in the variable. And so in our case, we know that it is going to be false because 7 is not strictly greater than 11. Right? And let's go ahead and print it out because we're going to print out more and more stuff as we go. So I'm going to go ahead and copy that line. And we'll also see another nice thing about the println and print commands is that when they're given a Boolean value, they print out the actual word. So true or false. You'll see the full text of it, and you can do what you want with that string representation of the word. Okay, so there's our first comparison. Let's try another one. Let's do something like, let's use the same variable. Eval is equal to, we'll say 15 less than or equal to 16. And we can see if we print it, we should hopefully all agree that it is true that 15 is less than or equal to 16. So we should see a true. And there it is. That's great. So let's try one more with just literals. Let's do something like eval is equal to 0 greater than 0. Right? And our question is this true or false? And we should say this is false. Right? Because 0 is not greater than 0. It's equal to 0, and that's a strict greater than, and so we should see false. Actually, let's do one more. This is another kind of easy one. Let's do 0 not equal to 0. And we should see true. Why should we see true? Because it is true that, we should see false. Excuse me, wow, I was wrong. It's false because it's false that 0 is not equal to 0. That's a true statement, right? So the answer should be false. My mistake. And there it is, right? False. So now let's try this with some variables. Let's make some integer or double variables. I'm going to stick with integers just because it tends to be easier to work with whole numbers. We'll say int x is equal to 10. We'll say int y is equal to 5. And now we can say eval is equal to, and I'm just going to kind of go full tilt, and we'll say y times 2 greater than or equal to, actually no, let's do equal to x. And then if we print this, what should we get? Hopefully you see it is true, and we need to discuss now precedence, because now it's suddenly there are more than just simple single operations, there are multiple operations. So before we say, I mean, it is true, but before we get into it, let's come back and consider our precedence operations. Think about it. In order to establish whether the left side is equal to the right side, we must know what the left side is evaluated as, and we must know what the right side is evaluated as. That would imply that our arithmetic operators are more important than our relational operators, because how can we relate two things if we don't know what those two things are? So if we were to write out our precedence order, and I'm going to go ahead and steal my list again from, I believe last time we had an updated one in compound operators. So here we go. Go and copy that and put this here. I'll put it at the top. There it is. And now we should see that the arithmetic is more important than the relational operators, but just as before, notice the assignment is last, because how can you store a value if you don't know what the value is? So assignment is still weakest, so that would say that we should be putting our number 6 as relational operators, right? So we're going to go ahead and say relational operators, or let's say relational. And so we'll say what are relationals: greater than, less than, greater than, equal to, less than or equal to, and not equal to. And these are all binary and left associative, right? We read from left to right just as if we were doing arithmetic. And so we should get true, because 5 times 2 is 10 is equal to 10, right? So we should see true as our last option. There it is. Well, let's try something a little more complicated. Let's do something like eval is equal to x times 3 divided by. Let's do this, sorry. Minus. So there we go. And again, this is a very long expression, and if we look carefully, we do see this relational operator in the middle. So we look at our arithmetic first on both sides, and then we establish each side as a value, and then we make our comparison, and then we store our answer. So you can, oops, I didn't do that. Let's copy the print. So go ahead and pause the video, evaluate it yourself, and then we can talk about what we expect to see as an output. So let's go ahead and start, and we'll say I'm going to start on the left side. And again, at this point, I'm not so picky that I need to do it exactly like the computer. I know that I should do my order of operations. Now, whether I complete the left side and then remember it and then do the right side, or if I do parentheses and then parentheses, at this point, it doesn't matter as long as I know that I'm doing it in the right order. So let's go ahead and try the left side. We do have parentheses, so it would be x times 3 divided by 2. X is 10. 10 is 10 times 3 is 30. 30 divided by 2 is 15. So 15 modulus y. And so 15 modulus y, 15 modulus 5 is 0, because 5 goes into 15 evenly. And then we have 15 plus 15 mod x. 15 mod 10 is 5, because 10 goes into 15 one time with the remainder of 5. 0 plus 5 is 5. So, and then times 5 times 5 is 25. So we end up with, on the left side, 25. So let's remember that we have 25 here. The right side, y mod 10. 5 mod 10 is 5, because 10 goes into 5 0 times with the remainder of 5. And then now we have 3 times x, which is 30. 30 times 5 is 150, minus 15 is 135. So our result is 25, and was it 25? I forget. But either way, it's a small number. I don't remember if it's 25, but less than, greater than or equal to 135. That is absolutely false. So we should get false as an answer. I don't know why I lost the number. And there it is, false. It was 15. 0 plus 5. 5 times 5 is 25. Yes, it was 25. So is 25 greater than or equal to 135? No, it is false. So therefore, we get false as our answer. And so again, the order of operations is preserved. And if we included casting and doubles, it would be the same thing, because according to our precedence, casting is more important than arithmetic. And so since arithmetic happens before relational, then casting must as well. We can put doubles and fractions and all those other things. We could put functions in there, square roots and so on, and it would be the same result. We would still have a Boolean answer at the end of the day. Okay, So that's essentially what we can do, and we can do many different examples. At the end of the day, it's a comparison between values. So we're going to continue with our logical operators, which are going to be used to kind of manage more complex statements, because even though this may look complex, it's really just a number compared to a number. But if I have multiple sets of numbers that I want to make comparisons and have them connected in some fashion, which is what we do in our regular reasoning all the time, then that is a little bit more difficult. So our logical operators are essentially how we combine individual Boolean expressions, individual statements of fact, whether they're true or false, combined together in some fashion. There are basically three things we can do, allow us for more complex Boolean expressions. So for example, if I had a statement that says, it is raining, and that is true or false. And I had a second statement, the temperature is below 32 degrees Fahrenheit, and that is also either true or false. I might want to ask the question, is it snowing? And so if we know about temperatures and how snow is made, we typically say that in most cases, snowing occurs when we have rain and a temperature is below freezing or 32 degrees Fahrenheit. And so that is a combination of two facts as being true or false. And in particular for snowing, it's a very strict combination. Both statements must be true. And we use the English word and all the time. We have another one that we also use, or. In fact, we used it in our less than or equal to, right? When we say or, we usually mean one thing or the other thing. English is a little bit different from the programming language, but we'll see in the more complete definition. But essentially, we're kind of saying, is it one thing or the other, or maybe both? And the last one is negation, which is flipping whatever it is. Whatever you say, saying not that, the opposite of that. So let's go ahead and write those. We're going to do two things. We're going to draw a truth table, which is kind of an expression of all the possible outcomes that a Boolean statement may have based on its inputs, and a Venn diagram, which also expresses that in a more visual way. So let's start off with negation. So logical operators. And we'll say logical operators manipulate or combine Boolean expressions into more complex Boolean statements. Right, so either they manipulate them because we might flip their answer, or we might combine them and then flip them, or any kind of mixing and matching of those things. So our first one, number one, is negation or not. Right, so I'll put not. So we say not something, not it is not raining, or it is not red, something like that. And the symbol we use in Java is the exclamation point, right? And so this allows us to say flip whatever the Boolean expression is. It is unary and it is right associative. So I'm going to go ahead and put that right. So let's go ahead and do our truth table for this and our Venn diagram. So I'm going to go ahead and switch to my Paint program, and we're going to try this out. So my truth table. And so a truth table, what we typically do is we express the possible values that are available to us, the different statements that may exist, and then what our goal is, and then we can kind of figure out exactly what the things are. And so in this case, since for negation, there is one single statement. We negate one statement at a time. So if I have a statement A, and that A could mean anything. It could mean it is raining. It could mean I have a soda. It could mean my dog is sleeping. It is a statement that has either a true or false evaluation. So for one statement, what are the possible things we could have? We could have true as a statement, or we could have false. And so what we're trying to evaluate is, what does the negation do? So if I say not, and I'm going to use the Java symbols, so we're saying not A, we're saying negation of A, whatever that statement is. So when it's true, what is not true? Well, that's an easy one. Not true is false. And when A is false, when it's not true, so what's not false? True. So we can see this is it. There's no other possibilities. Negation flips whatever the current Boolean value is. And so if we were to draw a Venn diagram, actually I'm going to use maybe this thing's a little thin. Do I have a better choice? No, I guess not. I'm going to draw my universe, right? Here's my universe of my Venn diagram. There's my universe. And here is our set A. And again, I call it a set because often this kind of stuff is considered set theory. But essentially we're saying this is the collection of statements A. Right? And so when we say A, we mean what's inside the circle. When we say not A, what would if I had to color in which part represents not A, that is everything that is not inside of A. So all of this. So if I color all of that in, again, I'm not going to do it all, but roughly speaking, everything that's not in the set A, that is not A. So this is the Venn diagram for the negation of the statement A, or set A. Right? A would just be the circle colored in. And so that's pretty simple. So let's go back and let's try this in Java. So let's go ahead and say, I'm going to make a new Boolean variable. I'm going to say Boolean negative is equal to, and I'm going to start it off as true. Or actually, let's just try it out. Let's put it in front. So let's do it with a literal first. And so with a literal, it is essentially flipping the value. So not true, the literal true is false. So if we print out the variable negative, we get false. And there's that last false. And then of course we can flip it, and I'm gonna flip it in a very particular way. I'm going to say negative is equal to not negative. Which again sounds strange, but if you think about it, we're saying take what it was and flip it, negate it again. So the negation of a false is a true. So if I print this, we should see true now as our last print, because I took the negative, flipped it, and reassigned it. Now, unfortunately, it would be really nice if we could do a compound assignment saying not equal to, but if we had a not equal to there, it would be a comparison. And so we cannot shorthand the logical not, or logical negation. So there it is, right? And so there's our negation. Very, very simple. Pretty easy and flexible. Anytime we have a statement, if we just want to say the opposite of it, we use negation. The next one, again, one that we use all the time, right? So I said it is snowing if it is raining and the temperature is below freezing, below 32 degrees Fahrenheit. So there's two statements in the binary operator of and, right? This is a very strict rule. It says both things must be true, and if both statements aren't true, then it's not snowing. So for example, if it's not raining, but it's 20 degrees outside, it's false that it is raining, and it is true that it's below 32. But it is not snowing. Why? Because as one of them is false, the whole statement as a unit is false. Or let's say it is raining, but it's 70 degrees outside. Then it is false that it's snowing, because both things must be true for it to be snowing. So let's write our truth table, and we can see the expression of all possibilities, because there's only two inputs, and so it's not too difficult to write a truth table for. So let's go ahead and say the and so and is also often called conjunction, right? This is a join of things. Or in our set theory, or in our Venn diagrams, we also call this the intersection. It's what's inside of both things, right? So intersection, right? And I'll say intersection is probably a more appropriate term, because a conjunction is a combination of two things, but it's maybe a little bit loose. So conjunction might be better for or, so we won't call it that. We'll call it the intersection of two things. Conjunction is more the or, and we'll get to that one next. So the intersection, and our operator in Java is two ampersands. If you don't know what an ampersand is, it is the and symbol. So some people call it the and symbol. It is shift 7. So two of these ampersand symbols next to each other. No space between them. A single ampersand has another meaning of something that we're not going to touch. But it does have a meaning, so we have to be very careful that we use two ampersands next to one another. So let's go ahead and try doing this. And it is left associative, and it is a binary operator. So I'm not going to write that it's left associative. So let's go to our back to our drawing. Let's make a truth table for the and operation. So in this case, my truth table is a little bit larger because I have a statement A and a statement B. There are two statements. And the result that I want to know our answer to is A. And, oh, sorry, my ampersands are terrible to draw. It's hard to do that. A and B. Or is the combination, the intersection of both statements true? And so what are the possible combinations of A and B we can have? Well, A can be true, or A can be false. So I'm going to have two of each. And then B can be true when A is true. B can be false when A is true. B can be true when A is false, and B can be false when A is false. So these are the four possibilities. Now I'm going to draw, before we fill it in, I'm going to draw the diagram, and I think it might give away what our answer to this is, and I think that's a better choice. So let's go ahead and draw our diagram. Here's our universe, all the things that exist. We'll put our statements A, or our set A, and we'll do our statements B. That's terrible. That's a terrible B. And then now, what is in? So we're saying it's very strict. The only thing that counts is what's in both. So if I'm in set A, I'm in this area, but not including the middle. If I'm in B, I'm in this area, not including the middle. If I'm in both A and B, then I'm here. So this section right here, if I color in the middle, that is the intersection. It's only when the statement or fact is both in set A or set B. That is a very, very strict rule. If you're outside of either set, it's not true. If you're in A only, it's not true. And if you're in B only, it's not true. So here we go. When A and B are both true, that means that the point is both in A and B. The result is true. It is raining and it is below 32 degrees. Therefore, it is snowing. How about when A is true and B is false? Again, the example we've been using, it's raining and it is below freezing. It is not below freezing according to this example, and therefore it is not true. Because this is like saying I'm over here. Am I in A and B? The answer is no, I'm not in the intersection. So this statement is false. Another one, when A is false and B is true. So again, it's not raining, but it is below freezing. So that's like if I'm over here. It's only freezing. Well, I'm not in the intersection, and therefore it's not true that it's raining. So this will also be false. And then the last one is when it's not raining and it's not below freezing. So that's somewhere else here. I'm out here in the universe anywhere at all. And the result is, since neither one of them is true, the entire statement is true. It is not snowing. Right? And so this applies for all statements that are Boolean. What the statements are is irrelevant to the logic. Right? Now, obviously, if you're having an argument or a conversation that requires certain facts to be established, what you're establishing is which of these rows you're in. Are the facts true or false? But that's not our concern here. Our concern is when these two facts are combined and we know what they are, can we establish what the resulting statement is going to be, true or false? And we can do that very easily by establishing whether we're here or if we're over here or wherever it may be. So let's go ahead and go back to our Java and see how this works. So here we go. We're going to go ahead and say Boolean and. And again, and is not a keyword, so we can make a variable called and, as horrible as that might seem. And let's go ahead and use our ampersands, our double ampersand as an and. So I'm going to do literals first, and then we can try out some other things. So we can say true and false. And if we print this out, we should see false, because true and false we said was false. Again, in real situations, you're not going to necessarily have literals every time. That's kind of a static statement, and it never changes. But if we did something like this, we said and is equal to eval and negative. And is a Boolean variable. Eval is a Boolean variable. Negative is a Boolean variable. A Boolean and a Boolean results in a Boolean. So is this true or false? Is this true or false? And the combination, the and, or the intersection of both, is that true or false? So eval, if we don't remember, the print that we had was that it was false because 25 was not greater than 135. So false and the negative was initially false. We negated it, so it became true. So false and true is false. So if we print this, we should get false yet again. And there it is. And now let's do one last thing. And here's, we're going to combine them. So here's, I'm kind of moving forward before we even do the or. But if we were to do and is equal to, actually, let's go ahead and do, no, let's just do true and negative. So a constant value or a set value, literal and negative. And we should get true as our answer, because true and negative was true is true, and there it is. And so again, what happens is often these things will be calculated either by variables being manipulated, or perhaps you have sensors in the real world that read in data. So you might have a temperature gauge, you might have a network connection that sends in data, a file that's being read. All kinds of things may happen that set variables up to be true or false, some logic, and then we can evaluate them and have our true or false based on what those things may be. So let's finish up by doing our last logical operator, the OR logical operator. So our third one will say or the union, or conjunction of two things, so intersection and union. And so or is the set of symbols that I'd say most people probably don't ever really touch. If you use Linux or Mac and you use the console, you may have used this symbol. Or you might use it for absolute values if you're typing. This is the only other reason I would see most people use it. But it's often called the pipe label or symbol. And this is shift /. So above the enter key, if you hold shift, it's a straight line. In some fonts, it's actually maybe two small lines that look like a break in the middle, but standing up straight. And so the or is two of these next to each other. And it looks even more like a pipe when they're next to each other. So those are the two pipes. That's or. And or is basically kind of the reverse or converse or inverse, well, I don't know which one is the appropriate word, of and. It's a lot more loose in what's allowed to be true. And and said there's only one time it's true when both statements are true. Or is going to say kind of the opposite. It says there's only one time it's false. And that's a very much more loose operation. And that's okay and can be very useful as well. And now here's where I'll point out where the English differs from the Java. Typically when someone says in English, I'm going to be home or I'm going to be at a party, right? Humans typically mean I'm at one place or the other, but not both, right? You can't be at home and at a party. I mean, maybe you can if the party's at your house, but in general, if it's somewhere else, we would say no, it's one or the other, but not both. But that is not accurate to what or in most programming languages represents. It's more, that's considered an exclusive or, a very strict or. The or we're talking about is one, the other, or both. So it is Sunday or I'm drinking a soda. As long as one is true, the entire statement is true. So if it's Sunday, it was true. If it's a Wednesday and I'm drinking soda, it was a true. The only time it's not true is if it wasn't Sunday and I wasn't drinking a soda. So they're very much inverse of one another, and the or is a lot more loose in what is allowed to be true. So let's go ahead and look at our truth table and our Venn diagram, and we can establish all the possible answers. So here we go. So I'm going to scroll down. I need to make myself some more space on my, come on, get bigger. A little bit more. Okay, so it's truth table. Same thing, or is binary, so there are going to be two inputs, A and B. And our statement in this case will be A or B. So the two pipes is the A. And so again, same thing. A can be true. A can be false. B can be true when A is true. B can be false when A is true. B can be true when A is false, and B can be false when B is false. That's all four possibilities. And so now let's show a diagram that'll hopefully help us clarify this. So here we go. Same thing as before. We have our universe, U, and we have one set and a second set, A and B. And so the or the union is very, very loose. It says as long as you're in one of them, or the other, or both, then you count. So here I could be anywhere inside this bubble, in this area. I can be anywhere in this area, which is great. And I can also be potentially in both. So essentially everything that's inside the circles in the sets is considered part of the union or the or of the statement. If you're anywhere else outside of that, then that's the only time that it's false. So if we said this, for example, it is Sunday or I am drinking soda. In this case, it's Sunday and I'm drinking a soda. Therefore, it must be true that the or is true. In this one, it's Sunday and I'm not drinking soda. Well, the question is it Sunday or am I drinking soda? And the answer is yes, it's Sunday. So it's also true. It's a very loose statement. It's like being in section A, but not in B. I'm still in the colored part, so it works out. How about it's not Sunday, but I'm drinking a soda? Then is it Sunday or am I drinking a soda? Yes. So it's also true. Very loose. That was like being in B. I'm here, so it counts. And the last and the only time is when I'm somewhere outside of here. It's not a Sunday and I'm not drinking a soda. That's the only time that the or is false. So it's very much the reverse of this one. This one is super loose in whether it's true or not. This one is super aggressive, where it can only be true in one point, or super loose when it's false. So pretty easy to deal with. Or is a very flexible thing, and so depending on what we're trying to express, we might use a mixing and a matching of these things. So let's try doing this with Java. So let's make another Boolean. We'll say Boolean or, and again, or is not a keyword, so we can give it a name like that. Not a great name, but reasonable for now. And we'll say something like negative or eval. So same thing as the one above, But now if we print this, and we run it, we should get true because negative was false. I'm sorry, negative was true and eval was false. True or false is true. So it's a very loose definition. And of course, I'll do one more just to try this out. And let's do something like or is equal to 10 greater than or equal to 5 times 2 or y mod 10 less than 0. And so if we print this, we can see we should get a true. And there it is, because 10 is greater than or equal to 5 times 2, which is 10. So 10 is greater than or equal to 10, so that's true. Or y was, I believe, we'll say y was, I lost it. Where's y? 5. 5 mod 10 is 5. Is 5 less than 0? No, that's false. So true or false is still true. As long as one statement is true, the or is true. And so that's what we get for our true, our last one. And there it is. Okay, so I'm going to stop this video. We'll continue next time with more examples. We'll use other data types. You've only used numeric data types. You've only used ints, but for doubles it's basically the same, but we haven't considered maybe strings, maybe chars, and other things, right? So we'll continue with that next time. I'll see you in the next video.